Welcome back to the Deep Dive, where we sift through the latest research and make sense of the cutting edge, all for you. Our eyes are remarkable organs, but they don't actually function like a digital video camera, constantly capturing full frames.
No, not at all. It's fascinating, isn't it? Our biological vision system is incredibly sophisticated, really efficient, and it's largely tuned to react to change.
Exactly. It's this activity-driven perception focusing on movement, on shifts, that's now inspiring a revolution in artificial intelligence. We call it bio-inspired vision.
Mm-hmm. And that brings us neatly to today's topic. We're diving into the world of event cameras. People sometimes call them silicon retinas, which is a pretty evocative term.
It really is.
Yeah.
So picture a camera that doesn't capture entire pictures, frame by frame like your
Wow.
phone camera. Instead, it's a sensor where each individual pixel acts almost like a tiny independent photoreceptor in your eye.
Right. And it only wakes up, so to speak, and records a minuscule event precisely when it detects a change in brightness. We're talking significant changes here, not just noise.
And the precision is just mind-boggling.
Yeah.
Microsecond precision.
Yeah, microsecond. That's the kind of temporal resolution we're dealing with. Now, what's truly fascinating here, and also, frankly, the source of a huge challenge, is that while these event cameras offer incredible advantages,
Advantages like?
well, you've got that super high temporal resolution we just mentioned, near zero latency, which is crucial for real-time stuff, an extraordinary dynamic range. They handle really bright spots and deep shadows way better than standard cameras.
Okay.
And because they only output data when something changes, they generate sparse data, meaning they use incredibly low power.
That sounds almost perfect. So what's the catch?
The catch is that they're fundamentally unique asynchronous data stream. It presents an immense hurdle for traditional AI models.
Because AI is used to neat packages.
Pretty much. Most deep learning systems, especially the powerful convolutional neural networks, or CNNs, that we've spent decades perfecting, they're inherently built for those neatly packaged, synchronized frames from conventional cameras.
All right, like a stack of photos.
Exactly. This event data, it's not just a slight tweak, it's like a completely different language of visual information. Continuous, asynchronous, sparse.
That's a critical distinction then. It's like trying to feed a continuous rapid-fire stream of individual musical notes, maybe just plinks and plonks, to an orchestra that only understands full, pre-written musical scores.
That's a great analogy. So the core question becomes, how do you take this continuous, incredibly granular, and let's be honest, often chaotic-looking stream of tiny events and translate it into something meaningful?
Something that deep learning systems can actually understand and use effectively.
Right. And crucially, how do you do this without needing what deep learning typically demands? Mountains and mountains of painstakingly labeled data.
Which for event cameras is almost impossible yet, I imagine.
Extremely difficult and expensive, yes. Which brings us to our mission for today. We're taking a deep dive into a groundbreaking approach called Event-LSTM. It was developed by Lakshmi Annamalai, Vignesh Ramanathan, and Chetan Singh Thakur.
Okay. Event-LSTM. And the goal?
Our goal is to unpack precisely how this innovative system converts those raw, sparse, asynchronous events into a rich, structured representation suitable for deep learning.
All while cleverly sidestepping that massive bottleneck of needing labeled data.
Exactly. That's the really exciting part.
So by the end of this deep dive, what should you, our listener, expect to understand?
Well, you'll get a clear grasp of Event-LSTM's key innovations and benefits. We'll explore how it enables powerful, unsupervised learning directly from these event streams.
Unsupervised meaning it learns by itself.
Essentially, yes.
Okay.
Without needing labels telling it, this is a car or this is waving. We'll also look at its remarkable ability to achieve speed invariant feature extraction.
The speed invariant. So it recognizes something whether it's moving fast or slow.
Precisely. And its exceptional energy efficiency, tying back to that low power advantage, this isn't just an incremental improvement, it's a fundamental leap.
A leap that's pushing the boundaries for things like object recognition, action detection, gesture recognition, making event cameras practical for stuff that was too complex before.
Exactly. It's opening up a lot of possibilities.
Okay, so let's unpack this. We've established event cameras are promising but challenging, a double-edged sword, as you said. To really appreciate what Event-LSTM does, we probably need to dig a bit deeper into how these silicon retinas actually work and why their way of seeing is so different.
Absolutely. The distinction is crucial. So, unlike your conventional camera capturing a full image, a snapshot of everything at a fixed rate like 30 times a second,
Right.
an event camera is fundamentally activity-driven. Imagine, like you said earlier, each pixel on the sensor is its own tiny independent detector. It's not passive.
Just waiting for something to happen.
Exactly. It just sits there monitoring its little patch of light. It doesn't generate any data until it notices a significant change in brightness crossing a certain threshold.
So it's not looking for what's there unchangingly, but specifically for what's changing, like the edge of a moving object.
Precisely that. If a pixel detects a brightness change above that threshold, up or down, then it generates an event. And this event isn't an image pixel value. It's a small packet of info.
The tuple you mentioned, XYTP.
That's the one. You get the XY pixel location, the super precise timestamp T in microseconds, and P for polarity. Is it getting brighter, ON, or darker, OFF?
Microseconds. That still blows my mind. Orders of magnitude faster than video frames.
It really is. And this activity-driven, sparse, asynchronous nature, that's where it just completely diverges from traditional cameras.
It's a minimalist approach then, capturing just the dynamic edge of protection, almost like a neural impulse rather than a full painting.
Well put.
And the advantages of this spark, not a painting approach are huge. Here's where it gets really interesting for applications, right? Robotics, high-speed automation.
Oh, definitely. That microsecond resolution means incredibly high temporal resolution and extremely low latency. So what does that mean for you, the listener, practically? It means they're perfect for fast-moving scenes where normal cameras just blur out or lag behind.
Like a drone trying to dodge obstacles quickly, or a robot trying to catch something.
Exactly. Think autonomous navigation in clutter, robotic arms needing pinpoint accuracy for fast movements. Every microsecond counts for those quick reactions. Traditional cameras just can't keep up in the same way.
The real-world impact seems enormous. Collision avoidance, maybe? Human-robot interaction that feels more natural because the response is instant?
All of that. And high-speed tracking for security or manufacturing quality control. Plus, it's not just about speed, they're incredibly efficient.
Because they only talk when something changes.
Right. Static scene. Virtually no data. This leads to that extremely sparse data stream, far fewer bits to process, transmit, store.
Which means much lower power consumption.
Drastically lower. Makes them perfect for things that need to run for a long time on a small battery. Tiny drones, wearable tech, remote sensors out in the field.
Things where you can't just plug it in easily.
Precisely. They only speak when there's something new or relevant to report.
And don't forget the dynamic range. My phone camera totally fails if I try to shoot a bright window with someone sitting in shadow. One part's blown out, the other's black.
Classic problem. Event cameras handle that much, much better. Because they respond to change relative to the current level at each pixel, not absolute brightness, they capture useful information across a vastly wider range of light levels. They're almost immune to being over or underexposed in the traditional sense.
Okay, amazing advantages. Speed, efficiency, dynamic range. So the but, why aren't these things everywhere already?
Well, the but is that unique data stream. It's just incredibly difficult for existing computer vision systems, especially deep learning, to use effectively.
Because it's not neat frames.
Exactly. It's
Yeah.
like asynchronous events popping off at different times from different pixels. It's continuous. It's unordered, really, just a stream of these XYTP tuples. It's utterly different from the structured image or video data that almost all our powerful AI models, especially CNNs, are designed for.
Right. A CNN expects a grid of numbers representing pixel values, all captured at the same instant. You can't just feed it this stream of time-stamped sparks.
You really can't. And the sparseness, while great for power, is also a challenge. You have fewer data points per moment compared to a dense image. Trying to build a picture from just a few flashing pixels is hard for algorithms designed for full images.
It's a fundamental data format mismatch, a translation problem.
A big one. Which raises the next question. How do we bridge that gap? Before deep learning really started tackling this specific problem, the main solutions were what we call handcrafted approaches.
And crafted, meaning people design specific algorithms to try and make sense of the event stream.
Pretty much. Brilliant people devised specific rules, clever math to convert that chaotic raw event stream into something more structured. Usually something that looked a bit like an image or a sequence of images that existing tools could then process.
Trying to turn the sparks into a picture, essentially.
Yeah, kind of. The main idea was to aggregate individual events onto a 2D spatial grid. Create a sort of pseudo-image. Think of it like making a heat map where recent activity is brighter, or maybe a trail showing where things have moved, transforming the temporal data into a spatial layout.
Okay. Are there well-known examples of that?
Oh, yeah. A very popular one is the time surface, often just called TS. Instead of storing brightness, a time surface grid stores a time value at each pixel.
A time value, how does that work?
When an event happens at pixel, x, y, that pixel's value on the time surface grid gets updated with the current timestamp, t. Then usually that value decays over time if no new events happen there.
So pixels with recent or continuous activities stay hot or have higher values.
Exactly. It effectively encodes a motion history or a recency map. Super useful for tasks involving motion analysis because it highlights where the action has been happening lately.
Clever. Were there other ideas like that?
Sure. Things like event images, which basically just summed up all events within a very short, fixed time window onto a grid, like a very quick, grainy exposure. Voxel grids took it 3D, accumulating events in space and time bins.
Okay, like a 3D histogram.
Sort of. And motion-compensated event images tried to subtract the camera's own motion to isolate the actual object movement. Lots of ingenuity went into these.
But the limitation was?
They were handcrafted. They required humans to design the specific conversion rules, which meant they could be quite rigid. A method tuned perfectly for one type of motion might perform poorly on another.
Like having a specialized wrench for every single type of bolt. Not very flexible.
Exactly. They often didn't generalize well across different tasks or scenes, and they were limited by whatever cleverness the human designer could come up with. They weren't learning from the data itself in the same way.
Right. Which brings us to the promise of deep learning, especially supervised deep learning. These models, like CNNs, are incredibly powerful for standard images because they learn features directly from data.
Phenomenally powerful, but, and it's a big but, they are incredibly data hungry.
Meaning they need tons and tons of labeled examples to learn properly.
Massive amounts. Millions of images of cats labeled cat. Countless hours of video with every object and action painstakingly outlined and tagged.
And for event cameras, getting that kind of labeled data is the major roadblock.
It's a massive bottleneck. Task-specific labeled event data is incredibly scarce, unbelievably expensive to create, and sometimes just physically impossible to get at the scale deep learning usually needs. Imagine trying to label every single microsecond event. It's a non-starter for most applications.
So without that ocean of labeled data, supervised deep learning struggles with event streams.
It struggles badly. The highly nonlinear, sparse nature of the data makes it easy for networks to get stuck in local minima during training if they don't have enough guidance from labels. They fail to learn robust, generalizable features.
Leading to poor performance and models that don't adapt well.
Exactly. Plus, early deep learning attempts, things like simple multi-layer perceptrons or MLPs, often just treated events individually. They completely missed the crucial sequential aspect. They lost all that vital timing information.
Right, it's the ends of the double.
Exactly. Later work started using LSTM's long short-term memory networks to try and capture that sequence, that memory. Even things like matrix LSTM, which used LSTMs on grids, were still mostly supervised. They understood time better, but still needed those labels.
Still stuck with a data hunger problem.
Fundamentally, yes. Which brings us finally to the core innovation here. Event-LSTM steps in with a genuinely different proposition, an unsupervised deep learning approach.
Okay, unsupervised, let's unpack that again. It learns without labels.
That's the key. It learns patterns, structures, dynamics directly from the raw, unlabeled event data itself. It's like teaching itself by observing the inherent correlations and sequences in the stream.
How does it do that? By observing.
By looking for statistical regularities, repeating patterns, the underlying structure of how events tend to occur together in space and time. For event cameras, where labels are the bottleneck, this unsupervised approach isn't just nice to have. It's potentially revolutionary, a real game changer.
And it's also task agnostic, he said.
Right. This means the representation it learns, they call it the LSTM time surface, or LSTM-TS, isn't specifically trained for one job, like only recognizing cars or only recognizing waving.
It learns something more fundamental.
Exactly. It learns a generic representation of the scene's dynamics, the underlying patterns. And this generic representation can then be fed into any downstream classifier or system for a specific task.
So you learn the general language of events once, unsupervised, and then you can use that understanding for lots of different specific tasks later, maybe with just a little bit of task-specific tuning or a simple classifier on top.
That's the idea. And if you connect this to the bigger picture for the listener, this tag-agnostic, unsupervised learning fundamentally eliminates that massive bottleneck of needing task-specific labeled data for the hard part, understanding the raw events.
Making event cameras way more practical for real-world use where labels are scarce or impossible to get. It democratizes the tech, in a way.
Absolutely. So how does it work? The core architecture is an LSTM-based autoencoder.
Autoencoder. Okay, that's the network that tries to copy its input to its output, right? Through a bottleneck.
Precisely. You have an encoder that takes the input and compresses it down into a smaller, abstract, latent space representation, a feature vector, and a decoder that tries to reconstruct the original input just from that compressed feature.
And the network learns by trying to make the reconstruction as perfect as possible, which forces the compressed part, the latent space, to capture the really important stuff.
You got it. It has to learn the essence of the input to be able to recreate it. Now, Event-LSTM applies this idea, but crucially, it uses LSTMs to handle the sequential nature of the event data at each pixel.
Because events happen over time, you need that memory component.
Wow.
LSTMs are good at sequences.
Exactly. LSTMs are a type of recurrent neural network, RNN, specifically designed to remember patterns and dependencies over long sequences. They have this memory that lets them process the flow of events, understand the sequence of changes, which is vital for motion.
Okay, so an LSTM autoencoder. Does it have one for every pixel? That sounds like a lot.
No, and this is a really clever design choice. They use a single autoencoder LSTM that's shared across all pixels.
Shared, why?
It's key for achieving translation invariance. Think about recognizing someone waving. If each pixel had its own separate brain, you'd have to teach every single pixel brain what waving looks like if it happens in its little area.
That sounds incredibly inefficient.
It would be. By sharing the same LSTM, the network learns the pattern of waving based on the local event sequence, regardless of where on the sensor that pattern appears. Top left, bottom right, doesn't matter. It recognizes the pattern itself.
Makes it much more robust and uses fewer parameters, fewer things to learn.
Way fewer. And the encoder part isn't just simple. It has multiple layers, 3 layers with different numbers of units. This lets it model the complex dynamicity, the intricate timing and patterns within the event sequences more effectively. It can capture richer temporal features.
And you mentioned the latent space. The compressed feature is just a single dimension. Why so small?
That's another deliberate, clever choice. It acts as a strong regularization. By forcing the network to squash all the important information about the event sequence at a pixel into just one number, it compels the network to learn only the absolute most salient, most meaningful feature. Discard the noise, keep the essence.
Like finding the single most important summary statistic for that sequence.
Kind of like that, yeah. So during training, the encoder learns to generate the single meaningful feature, the LSTM-TS value, from a pixel's event sequence. The decoder then tries to recreate the original event sequence just from that single number.
And the system learns by minimizing the difference between the reconstructed sequence and the original.
Exactly. Minimize the reconstruction error. The final output, the LSTM-TS, is then a 2D grid, the same size as the sensor, populated with these learned, single-dimensional features at every pixel location where events actually happen.
And it stays sparse. It only computes features where there are events.
Yes, critically, it maintains the sparsity. No events at a pixel, no computation, no feature stored there. Keeps it very efficient.
So how does this compare to something like matrix LSTM that you mentioned earlier?
A key difference is that Event-LSTM uses this multi-layer encoder-decoder structure within an unsupervised autoencoder setup. Matrix LSTM was more focused on using LSTMs in a supervised context.
Ah, so Event-LSTM learns the representation without labels, making it much more practical.
Precisely. It learns robust features directly from raw, unlabeled event streams, making it far more applicable to diverse situations where you don't have those big labeled data sets. It learns the grammar of events itself.
Okay, that makes sense. Now, you also mentioned another clever twist, asynchronous windowing. It doesn't process the whole stream at once.
Right. Trying to feed an entire, potentially very long event stream into an LSTM all at once is computationally heavy and risks losing information from the beginning of the sequence, the vanishing gradient problem, among others. So Event-LSTM breaks the stream into smaller temporal windows or sequences.
Like looking at short snippets of activity.
Exactly. Focus bursts. This helps the LSTMs keep track of local timing details and makes processing long streams manageable. But here's the really crucial distinction, the truly novel part, how it creates those windows. Synchronous versus asynchronous sampling.
Okay, this sounds important. Synchronous is the old way.
Synchronous, or sync, is the traditional way. You form sequences based on a fixed time interval. Say you collect all events that happened in the last 100 milliseconds, that's one window. Then the next 100 milliseconds, that's the next window, like taking snapshots at regular time intervals.
Makes sense. So what's asynchronous?
Asynchronous, or async, is Event-LSTM's novel approach. Here, sequences are formed based on a fixed number of events. For example, you wait until exactly 10,000 events have accumulated, regardless of how long that took. That collection of 10,000 events forms one window.
Wait, so the time duration of each window can vary wildly. If things are happening fast, 10,000 events might occur in just a few milliseconds. If things are slow, it might take a whole second.
Precisely. And this raises that key question. Why would fixing the number of events be better than fixing the time? It seems odd at first.
It does. Why ignore the clock?
Because it gives you two incredibly powerful advantages. First, and this is huge, speed and variance. Here's where it gets really interesting.
Okay, I'm listening.
Imagine you're watching someone wave their hand. If they wave really fast, a fixed time window, say 100 meters, might only catch a small part of the motion, maybe just a few events in that quick burst.
Right.
If they do the exact same waving motion, but really slowly, that same 100 meters window might capture loads more events, showing a much longer segment of the slow movement.
So the data inside the fixed time window looks completely different depending on the speed, even for the same action.
Totally different. Which means the features your AI extracts will be heavily dependent on speed. This makes it really hard to reliably recognize waving if it can happen at any speed. You get high intra-class variance, the same class looks very different.
Okay, I see the problem. So how does async fix that?
The asynchronous window, remember, collects a fixed number of events, say 10,000.
Wow.
So whether the hand waves fast or slow, the window always contains the same amount of activity, 10,000 events worth of motion description.
So the content of the window represents a similar chunk of the action pattern itself, regardless of how stretched or compressed it was in time.
Exactly. The features learned from that window describe the pattern of motion itself, largely independent of how fast it happened. You can recognize the wave, fast or slow, because the underlying pattern captured by those 10K events is similar.
That is really clever. It decouples the pattern from the speed.
It does. Figure 2 in their paper shows this really well. It plots the time taken for 10K events for different actions in a dataset called UCF101-DVS. You see huge variations in time within the same action class, proving the async approach captures dynamics independent of speed. It leads to much more robust recognition.
Incredible. Okay, that's speed and variance. What's the second big advantage of async?
The second is energy-saving feature extraction. Because async sampling only triggers processing when a certain number of events have arrived, it's inherently demand-driven.
Meaning, if nothing's happening, it just waits.
Exactly. If the camera's looking at a static scene, very few events are generated. The system just sits tight, waiting for that 10,000th event. It's not constantly processing empty or near-empty time windows, which is what sync sampling would do.
Which would be a total waste of power and computation.
A huge waste. Async avoids all that redundant processing. It generates LSTMTS outputs only when there's enough new information to warrant it. It generates non-redundant outputs.
Making the whole pipeline much more energy efficient.
Highly energy efficient. And they show this too. Table I and Figure 3 in the paper demonstrate that async mode consistently generates fewer LSTM-TS frames and needs less processing time compared to sync mode, especially for dynamic things like action and gesture recognition. It's just smarter processing.
Okay, so this Event-LSTM approach, unsupervised, task agnostic, using this clever async windowing, sounds theoretically brilliant. How does it actually perform?
Good point. Yes, they mention mitigating background activity, BA noise, those random events that pop up even with no real change, maybe due to sensor heat or imperfections. They used a spatiotemporal filter to clean the data up first, ensuring the input to Event-LSTM was focused on genuine scene changes.
Makes sense.
Okay.
Okay, so scenario 1, testing it in an end-to-end unsupervised setting, the situation where you have very few labels.
Right, this is designed to validate its core promise. The setup is Event-LSTM, trained unsupervised, generates the LSTM-TS representation. This representation is then fed into a pre-trained MobileNet.
MobileNet, that's a standard efficient CNN for image features, right?
Exactly. It's good at pulling spatial features from grid-like data. Then the features from MobileNet go to a simple support vector machine, an SVM, for the final classification.
And the key is only the SVM needs some labels.
Precisely. And because an SVM is a shallow classifier compared to a deep network, it needs significantly less labeled data to train effectively. The heavy lifting, the complex feature learning from events, is done unsupervised by Event-LSTM. Labels are only used for the final, simpler step.
Very clever pipeline. So how did it do on action recognition?
They used the Davis 346 dataset, 12 actions, 15 people, office environment. First, comparing sync versus async within Event-LSTM. The results were really striking.
Probably sync was better.
Consistently better. Table I shows asynchronous mode having a higher F1 score. That metric balancing precision and recall across most activities shows that speed and variance really helps.
And it was more efficient too.
Yep. Async generated fewer LSTMTS outputs, needed less processing time. Win-win. Then they compared Event-LSTM async against other unsupervised state-of-the-art methods.
Like those handcrafted features, SAE, SNN, event counting.
Those exact ones. And Event-LSTM significantly outperformed them according to Table 2. It really shows the power of learning the representation versus hand designing it.
Okay, clear win for unsupervised action recognition. What about gesture recognition? Gestures can be subtle, maybe even more speed-dependent.
Good question. They used a dataset with 11 hand-arm gestures. And crucially, to simulate having minimal labels, they only used a small fraction of the available data, just 319 instances out of nearly 1,600.
Really pushing the low data scenario.
Exactly. And again, the results mirrored the action recognition findings. Asynchronous Event-LSTM generally performed better than synchronous, Table 1, handling the speed variations and gestures well, and it again significantly surpassed the other unsupervised methods, Table 2. It proved robust even for these finer movements with limited labeled examples.
That's really compelling for the unsupervised low-label case. But what about the other angle, using Event-LSTM to enable those powerful, data-hungry supervised deep learning models, Scenario 2?
Right. Can Event-LSTM act as that bridge, translating events into something a standard CNN can handle effectively?
The universal translator idea.
Exactly. They tested this on complex action recognition using a much harder dataset. UCF 101 DVS, this one has over 13,000 videos across 101 different action classes. A real challenge.
101 classes, okay. And the setup.
LSTMTS generated using async mode, 10K events per window, was fed into a fine-tuned mobile net, the one pre-trained on ImageNet. So using the event LSTM output as the image input for the CNN.
And the result.
Very good accuracy. They achieved a 77.6% F1 score, which is really impressive for this complex dataset. Table 3. This performance was competitive with, or even better than, some specialized models like graph convolutional networks or 3D CNNs designed for standard video.
Wow. So the translated event data was rich enough for a standard CNN to perform really well.
It seems so. And again, Figure 2, showing the speed variation within classes for this dataset, reinforces why the async approach was likely key to achieving this. It handled the inherent speed variability successfully.
Okay, solid performance on complex actions. But what about object recognition? This is where the task-agnostic claim really gets tested, isn't it? Does it work when the main clues aren't about motion patterns?
This is a critical test, and the results are fascinating. They used the NCARS dataset, first basically telling cars apart from background scenes. Importantly, this data came from an ADAS sensor, a different type of event camera than the DVS sensors used for the action dataset.
Different task, different sensor, good test.
And they did a clever experiment. They compared two Event-LSTM models. Model 1, MUCF, was trained only on the UCF 101 action data. It had never seen a car or an ADAS sensor event before.
Okay.
Model 2, MNCARS, was the same base model, but then fine-tuned specifically on the NCARS data.
So one model was completely naive to the task and sensor, the other was specialized. What happened?
This is where it gets really compelling for the task-agnostic idea. What stands out is that model MUCF, the one that had never seen object data or ADAS data during its unsupervised training, performed almost equally well as MNCARS, the one fine-tuned for the job, Table 4.
Get out. Seriously. The action-trained model did almost as well on car recognition.
Almost identically well. It's powerful evidence that Event-LSTM learned a truly general representation of visual structure and dynamics from the action data, a representation so fundamental that it transferred almost perfectly to a different task, object recognition, and even a different sensor modality, ATIs.
That really backs up the task-agnostic claim. It learned something universal about events.
It strongly suggests that. And when they compared Event-LSTM async against other state-of-the-art methods on NCARS, Total V, it beat handcrafted methods, graph networks, and even some fully supervised architectures that didn't properly handle the event memory.
Better than supervised methods in some cases. That's impressive.
It highlights that getting the representation right for event data, including the memory, might be more important than just throwing supervised labels at a poorly suited architecture.
Okay, one more test. They really pushed it within Caltech 101, right? Even more complex object recognition.
Yeah, and Caltech 101 is a beast. 101 object classes challenging data. Here, they used async LSTM-TS with 20K events this time, fed into a fine-tuned ResNet 18, a deeper CNN.
Or is that 18? Okay.
And to give it a bit more context, they use 3 consecutive LSTM-TS outputs stacked together as input channels for the ResNet.
Like a mini movie of event activity.
Kind of, yeah. A very short sequence. And the results, state-of-the-art accuracy. What's remarkable, as they note in Table 6, is that even though Event-LSTM itself is an unsupervised generator, the whole pipeline performed only slightly worse than the very best fully supervised methods designed specifically for event representation on this benchmark.
So it almost closed the gap between unsupervised and supervised performance, even on this really hard object recognition task.
Pretty much. A huge achievement, showing the power and maturity of this unsupervised approach combined with standard CNNs.
Okay, let's try and wrap this up then. After diving deep into Event-LSTM, what are the really big takeaways for you?
Well, first and foremost, it powerfully demonstrates the viability and, frankly, the necessity of unsupervised learning for making event cameras practical. It tackles that core data hunger problem head on.
Showing that machines can learn the language of events without needing endless labeled examples.
Exactly. Second, that asynchronous sampling technique is just brilliant. It's a real game changer.
Giving you both speed and variance, recognizing patterns regardless of speed and huge energy savings by processing only when needed.
2 massive wins. Third, it successfully bridges the gap between the new world of event sensors and the established power of conventional CNNs.
Acting as that translator, turning sparse async events into a grid that CNNs understand.
Right, unlocking the potential of existing deep learning tools for this new domain. And fourth, its versatility, proven effective across motion tasks, appearance tasks, and even different sensor types. Truly task agnostic seems fair.
So connecting this to the bigger picture, Event-LSTM isn't just another small step.
Yeah.
It feels more like a fundamental shift in how we can process event data.
I think so. It's making advanced, efficient, robust vision possible in ways that were previously just too hard or too expensive due to the data challenges. Think tiny robots, high-speed monitoring, low-power wearables.
It empowers machines to learn to see the dynamic world, the world in motion, with incredible efficiency and adaptability, without needing humans to hold their hands the whole way with labels.
That sums it up nicely. It's a significant step towards more autonomous and intelligent visual perception.
So what does this all mean for you, our listener? Consider the implications. A camera that sees change, not just snapshots. An AI that learns from that change without being told what to look for or how fast it might happen. How could this tech, with its low power, high speed, and unsupervised learning, impact the future design of, say, autonomous vehicles, making them maybe react faster, more reliably in unpredictable situations?
Or think about smart home devices. Could they become more aware of what's happening, more responsive while using barely any power? Or even medical diagnostics may be detecting subtle, rapid changes that indicate a health issue.
It really opens up possibilities, which leads to our final provocative thought for you. What kind of completely new discoveries or applications might emerge when machines can truly learn to see the world in motion, not just static frames, and do it with this kind of remarkable efficiency and self-sufficiency? When they don't need us to label every little thing, what new insights might they uncover about the dynamic world around us?
It's exciting to think about where this could lead.
Absolutely. Thank you for joining us on this deep dive into Event-LSTM. We hope you gained some valuable insights into the future of AI vision. We'll see you next time on The Deep Dive.